Hello students, welcome back to the JEE Last Mile Preparation Series 17. Today we will take up questions 33 and 34. But before I do that, by now you already know that I'm Sujata from CBSE NEET, jeechemistry.in, and we are bringing you 2 questions every day until April 4th to help students get that extra edge for their JEE chemistry exam preparation. So, to keep me motivated in this task, please hit the like button and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. Let's get started. We continue with inorganic chemistry, and today we will take up 2 questions from S block elements. So here is question number 33. Which of the following is incorrect? So we need to identify amongst these 4 options an incorrect statement. Now analyzing these options will help you to recollect a lot of periodic trends that you've studied in S block elements. Okay. The first option A states that the solubility decreases in the order beryllium sulfate greater than magnesium sulfate greater than calcium sulfate. Okay, so let's analyze the option A first, and then we will move on to the various options one by one. Okay, so now moving on to solubility. Now, when we discuss solubility, the 2 factors involved in solubility would be 2 competing factors involved in solubility would be the enthalpy of hydration, okay, and the lattice enthalpy. Okay, so lattice enthalpy gives you the strength of the bond between the cation and the anion. Hydration enthalpy gives you the amount of energy released when a cation or an anion are surrounded by what? The solvent molecules, water molecules. So the size of the cation is very important to identify the magnitude of hydration enthalpy. All right. So going back to the option A, you notice that down group 2, so beryllium, magnesium, and calcium, they all belong to group 2 of the periodic table. So beryllium ion, magnesium ion, and calcium ion. Sulfate ion is large, right? So what happens here is the beryllium ion is the smallest, right? Beryllium ion is the smallest. So let me write that here. The beryllium ion is the smallest ion, smallest cation, right? And then we have magnesium ion, and then we have the last one, which is the calcium ion. Now, calcium ion is the largest cation in this list. Okay, so based on the size of the ion, this will have the highest hydration enthalpy. This will be the largest. Most amount of energy is released when beryllium ion is surrounded by water molecules. So hydration enthalpy is the largest for beryllium ion. Okay, what about lattice enthalpy? Now lattice enthalpy, beryllium ion being the smallest. So that's another important discussion. Okay, so when we are discussing the lattice enthalpy, all right, now beryllium ion being the smallest cation, but the anion sulfate ion is common for all the 3 sulfates, right? So beryllium ion being very small can polarize the anion. So polarization of the anion will occur. When polarization happens, this will break down. The lattice enthalpy becomes less. So lower lattice enthalpy. That is because beryllium ion shows covalent properties. The beryllium shows covalent properties. So lattice enthalpy is low for beryllium sulfate because of the small cation. All right. So smaller the cation, greater the polarization of the large anion. If the anion is large, this is how you explain the trend in lattice enthalpy. So as you move from beryllium sulfate to, let me go to the next page. So as you move from beryllium sulfate to magnesium sulfate to calcium sulfate, what do you notice? The hydration enthalpy is found to decrease. So what is increasing here is the lattice enthalpy. Lattice enthalpy increases from beryllium sulfate to calcium sulfate, whereas the highest hydration enthalpy is seen for beryllium sulfate. Okay, so this is the smallest lattice enthalpy. Lattice enthalpy is the least for beryllium sulfate, right? Least for beryllium sulfate. Hydration enthalpy is the most for beryllium sulfate, correct? So because of that, the hydration enthalpy is the energy released during hydration enthalpy far exceeds the lattice enthalpy. So hydration enthalpy is what is the dominant factor for beryllium sulfate. What does that result in? Beryllium sulfate will be the most soluble in water. Okay, so solubility will decrease from beryllium sulfate to magnesium sulfate to calcium sulfate. Okay, so these are the two the enthalpies which will decide this particular statement. So going back to the question, we notice that option A is correct. Okay, now let's move on to option B. In option B, we deal with the thermal stabilities: beryllium carbonate, magnesium carbonate, calcium carbonate. Now, thermal stability also depends upon lattice enthalpy. So option B, thermal stability depends upon lattice enthalpy. Okay, so if you notice, you have beryllium carbonate. I've already explained this in the previous option. Then we have magnesium carbonate, and then we have calcium carbonate, right? Beryllium ion being the smallest, beryllium ion being the smallest, the polarization power or the polarizing power will be high. High polarizing power. And when the polarization power is high, the beryllium carbonate will have the least lattice enthalpy. Least lattice enthalpy signifies or implies what? The least thermal stability. Okay, so beryllium carbonate will be the least stable. Beryllium carbonate will be the least thermally stable. On heating, beryllium carbonate will decompose most readily. The decomposition temperature of beryllium carbonate will be the least because of its very low lattice enthalpy. Why is the lattice enthalpy low? Because of the size of the cation. Carbonate ion is a large anion. So whenever the cation is very small and the anion is large, polarization power is high. So beryllium cation will pull the electron cloud of carbonate ion towards itself. So beryllium carbonate, therefore, will, so this is beryllium ion, right? Beryllium ion. Carbonate ion is this, OC double bond O minus. This is carbonate ion. So what will happen is the beryllium ion being very small and the carbonate ion is large will pull the O minus towards itself, resulting in the breaking or the weakening of the CO bond. And that will result, and this happens on heating, this will result in giving you the products beryllium oxide plus carbon dioxide. Okay, so the temperature at which beryllium carbonate decomposes is very low. The moment you heat it, beryllium carbonate will decompose to give you beryllium oxide and carbon dioxide. So it is the least thermally stable. Okay, so going back to the option B is also correct. Okay, now moving on to option C, melting point. That is an easy discussion. For melting point, you look at the strength of the bond, the extent of electrostatic force of attraction between the cations and the anions. Okay, so if you look at sodium chloride, potassium chloride, rubidium chloride, cesium chloride, we'll discuss lithium chloride a little later. So as you go down group 1, the size of the cation will increase. As the size of the cation increases, the electrostatic force of attraction between the cation and the anion will decrease. Correct? So sodium chloride will be the most ionic, right? Most ionic, strongest electrostatic force of attraction between sodium ions and chloride ions. Highest lattice enthalpy. So melting point depends upon lattice enthalpy, right? So the lattice enthalpy depends upon the size of the ions. If the anion is the same, the cation is increasing in size. Smaller the cation, greater the electrostatic force strength between the cation and the anion. And all the cations have the same charge. So size is the determining factor. But if you look at size, the lithium chloride should have been the most ionic, right? Lithium ion is the smallest, but the problem is lithium ion is very small, but the chloride ion is large. What can that result in? Again, polarization effect. And that is why lithium chloride shows some covalent character. Understood? So it's not a pure ionic compound. So because of that, its melting point will be lower or the least amongst the melting points of the other group 1 chlorides. Okay, so option C is also correct. Now we move on to option D, which deals with the reducing character. That requires some explanation. Okay, so we are now discussing option D, which is the reducing character. Now, what do we mean by reducing character? Reducing character implies ability to act as a reductant or a reducing agent. So these terms can confuse you at times, and that's why I'm listing out all the points in the same order. Okay, so reducing character implies ability to act as a reducing agent. Okay, now ability to act as a reducing agent will be high if there is greater ability to lose electrons, right? So greater the ability. So before that, ability to act as a reducing agent implies ability to get oxidized, right? Whichever species gets oxidized will act as the reducing agent. Ability to get oxidized implies ability to lose electrons, right? So next point in the order. Greater the ability to lose electrons. So what decides the ability to lose electrons? Which periodic property determines the ability to lose electrons? I'm sure you remember that. Ionization enthalpy. So ionization enthalpy or ionization energy should be less. Correct, lesser amount of energy should be absorbed to remove the most loosely bound electron from the gaseous atom. So next point in that order would be lower the ionization enthalpy, greater the ability, right? Greater the ability to lose electrons or to get oxidized. And hence, stronger the reductant or the reducing agent. Okay, so this is the connection between ionization enthalpy, ability to get oxidized, and the strength of the reducing agent. So it looks as though ionization enthalpy is the only factor which determines the strength as a reducing agent. If ionization enthalpy was the only factor, then this particular order would be correct. Lithium would be the least reducible. Lithium would have the least reducing character or would be the weakest reducing agent because it has got the highest highest ionization enthalpy in that particular group. So as you go down group 1, since the size of the cation increases, the ionization enthalpy will decrease. So lithium ion will have the highest lithium ion will have the highest ionization enthalpy. Ability to lose electrons will be the least for lithium atom, right? So lithium will have the highest ionization enthalpy. We're talking about the first ionization enthalpy alone, ability to lose one valence electron. And cesium, being the largest alkali metal, will be so large that the outermost electron can be easily lost. So cesium will have the least ionization enthalpy, and therefore cesium is expected to be the strongest reducing agent. Correct? Now what is observed is lithium is the strongest reducing agent. Okay, so why does lithium play the role as the strongest? How do we explain the strength of lithium as a very powerful reducing agent? So that is the discussion here. Okay, so I hope you've understood the initial discussion. Now let's focus on the reduction potential. So let me write down the equation here. A metal in the solid state will lose an electron to give you the metal ion, okay? And in aqueous medium will be metal ion in the aqueous medium. So when we talk about the reducing character, we imply the reducing character in aqueous solution reactions, right? So reactions imply aqueous medium. So aqueous medium. So this is the reaction. So this is oxidation. Okay, the forward reaction is oxidation and the backward reaction is what? Reduction. So you're aware of that. This is oxidation and the backward reaction is reduction. Okay, so now for this process to happen, the first step is for the metal to get converted into the gaseous state. Now, what do we call this? This is atomization or sublimation. Sublimation enthalpy. All right. Now, once the metal is in the gaseous state, this gaseous metal atom will now lose one electron to form a metal ion in the gaseous state. And this is ionization enthalpy, the first ionization enthalpy. So once we get the metal ion in the gaseous state, next step to convert the metal ion in the aqueous state, we call, in the presence of the medium, aqueous medium, we call it as hydration enthalpy. Hydration enthalpy. All right. So now, if you look at sublimation and ionization enthalpy, both these are endothermic, right? Whereas hydration enthalpy is exothermic. So the magnitude of the amount of energies absorbed during sublimation and ionization will compete with the magnitude of energy released during hydration. Okay. So in the case of lithium, what is happening is lithium ion being the smallest, its hydration enthalpy will be so high, will be so highly exothermic. Okay, will be highly exothermic and exceeds the magnitude of ionization enthalpy 1 plus sublimation or atomization enthalpy. Because of this reason, because of the highly exothermic value of the hydration enthalpy, that is the reason why lithium plays the role as the strongest reducing agent. So the amount of energy released during hydration far exceeds the amount of energy absorbed during sublimation and ionization, first ionization for lithium. As a result of which, lithium ion in the aqueous solution is produced with the release of a very high amount of energy. Okay, so because of that, what happens is the forward reaction. So what happens here? Because of all this, because of the high magnitude of this factor, the oxidation potential of lithium atom will be high. Okay, that's why it has got a very low reduction potential. Lithium ion has a very low reduction potential. If the forward reaction is high, the backward reaction will be low. So forward is oxidation. So oxidation potential of lithium is where lithium solid is very high once lithium enters into a reaction in aqueous medium, all because of the high hydration enthalpy of lithium ion. Okay, so because of that, this particular statement is wrong. So this is the incorrect statement, or we want an incorrect statement. So option D is the correct answer. So this required a lot of explanation, and because we discussed each of these options independently, I hope you've been made to recollect all the important factors that you have learned, all the important properties that you have learned in the chapter S block elements. All right. Now moving on to question number 34. Okay. Now, in question number 34 is a very easy question. Which of the following group 2 metal hydroxides will be the least basic? Okay. Hydroxides, so it becomes very easy for us to understand the basic character of hydroxides. whichever has got the highest ability to produce OH minus most readily will be the most basic. Okay, so let's look at the main factor here again would be the size of the cations. So if you look at the size of the cations, size of group 2 cations. Okay, what do you notice? Size of group 2 cations. The size of magnesium ion would be the least, right? Magnesium ion smaller than calcium ion, smaller than strontium ion, smaller than barium ion, right? So barium ion being the largest, what largest cation in group 2, what can happen? The BAO bond, this bond will be the weakest. This bond will be the weakest bond. And when the bond is the weakest, that bond breaks most readily. There are most readily to produce what? So let me write down this. So you have the BAO bond, correct? BAO bond. OH and another OH, correct? So the BAO bond is the weakest bond because of the large size of the cation. As a result of which, barium hydroxide in aqueous medium will readily dissociate to give you Ba2 plus aqueous plus 2 OH minus aqueous. So this will occur most readily. Most readily. And because the OH minus ions are produced most readily by barium hydroxide will be the most basic. And the least basic will be magnesium hydroxide. Why? Because of the small size of the magnesium ion. This is the smallest cation in group 2. Okay, so option D would be the correct answer. If you found today's video helpful and useful, please like the video and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. See you tomorrow.